This video will discuss how we find rate laws for a given chemical reaction. So if we have our standard reaction here, reactants A and B, products C and D, each of them has a stoichiometric coefficient, nu A, nu B, nu C, nu D. So we know we have some rate law, which depends on the concentration of our reactants to some given power times the rate constant. So our rate of reaction V of T equals K times A to the MA times B to the MB. Our question is, how do we find these orders for each of our reactants? Because as we've mentioned, they're not necessarily equal to these stoichiometric coefficients. They can be any value, but typically they're integers that are either 0, 1, or 2. Although they can be half integers or other odd values. Okay, so there's two kinds of main reactions, among others, that we can use to find these rates. One is called the method of initial rates, where we look at the initial rate, so the V at T equals 0. Another would be called the method of isolation, where we take one reactant and we overwhelm or saturate the system with it such that its concentration doesn't change over time. So for the first case, we might look at the method of initial rates. V1 of 0 equals K times A naught to the MA times we have some given concentration of reactant B, B1 to the MB. V2 naught is equal to K times we have the same concentration of A, and then we have a different concentration of B. So we're going to look at how this initial rate changes using this concentration of B versus this one. So looking at T equals 0 would be the method of initial rates. Alternatively, what we could do is we could make the concentration of A huge, then the rate constant times the concentration of A to its rate power is approximately a constant, because if A is much, much greater than B, then B is the limiting reagent, and we're not going to change the concentration of A much over the reaction. So what happens here is the concentration of A is basically constant, and we treat Ka to the Ma as basically a new rate constant called K prime. Okay, so in either case, what we end up getting is two different velocities of reaction, or two different rates of reaction for two different concentrations of B. So V over B, concentration of B1 equaling, this should be V over the concentration of B1 to the MB, yes, equals V2 over B2 to the MB. Okay, so I can rearrange that to look like rate 1 divided by rate 2 is equal to the quantity concentration of B1 divided by concentration of B2 to the power MB. If I take the natural log of both sides, log of V1 over V2 equals MB times natural log of concentration of B1 over concentration of B2. So the order of our reaction in reactant B is equal to the natural log of our first reaction rate divided by our second reaction rate divided by the natural log of our concentration of our reactant in reaction 1 divided by our concentration of our reactant in reaction 2. So this is one way to do it using these two methods. There are also a wide variety of others you could use. One caveat to note here is that in order to do this, we need to assume that the reactants are mixing instantly, which means that they're mixing within about a millisecond or so. This can be a problem if our rate constant is too fast that the reaction occurs before we have thorough mixing. So what we're assuming here is that the reactants are going to mix thoroughly, and then they're all spread out at an equal concentration, and then our rate constant can be measured. If our rate constant is on the order of the time it takes to mix, then we have to go about other ways of finding our reaction orders, and these aren't going to do us any good because we're reacting too quickly to get these varying reaction rates as we change the concentration.